In this video, I'm going to look at the two examples from the module of linear growth dealing with the elk population and the gasoline example. So let's take a look at those live so you can kind of see me working through the ideas. So here's the setup for the problem. The population of elk in a national forest was measured to be 12,000 in the year 2003 and was measured again to be 15,000 in 2007. Okay, so it seems to be growing. If the population continues to grow linearly at this rate, what will the elk population be in 2014? Well, I know that the problem is not real because in the real world, populations like this don't grow linearly, and they certainly just don't grow forever. They would kind of max out for one reason or the other. Usually, it's that wherever the animals are, the land can only support so many, right? So we'll have a maxing out of the population. But just for a moment, let's suspend that idea, and let's just assume that this could actually happen. Okay, so in the year 2003, we have 12,000. So you might even organize your thinking something like this. Okay, we have year, we have 2003, and our population of our elk, I'll put it over here, kind of in a table format, right, is 12,000. That's kind of where we're starting the issue off. Now, we don't have any information about 2004 or 2005 or 2006 or 2007, right? Oh, actually, I'm sorry, we do have 2007. That's the first time we have more information. It's now 15,000. Now, if it's growing linearly, that means it's growing at the same rate every year. You could probably think about it, go like, okay, let's see. 2003 is 12,000. Maybe the next year it's 13,000 and then 14,000 and then 15,000. Oh, that would be one off. So this number is a little tricky to figure out. How would we get from here to here, from here to here, from here to here, and from here to here? You'd have to find a number that works. Okay, so one way to think about it is, okay, how much did I change from the beginning, right, to the ending? Well, my population went up, right? 3,000. And then how long did that take? Well, that was from 2003 to 2007 in 4 years. So then if you just use a little division, if you think, okay, there's 3,000 elk divided by 4 years. Let me grab my calculator. 3,000 divided by 4, 750 elk per year. Okay, so that would be my D. My D is 750. That's my change. And my other information is given right in the problem. So let's take a look at the two recursive forms. The first one, P sub n equals P sub n minus 1 plus D. Okay, so recursively, to find the number of elk, you just take the previous year, or the previous year, and you add this number that we found, 750, to it. Now that works well and fine. We could even populate our table that way, right? We would say, oh, okay, well then in 2004, there must have been 12,750. The following year, there must have been 13,500 by adding another 750. The following year, there must have been 14,250. And then we have 15,000. And so we could keep doing that to figure out how many there are in 2014, right? By going 7 more years all the way down to 2014. But let's go ahead and take a look at the explicit formula, because I think that's probably a better way to do it. So the explicit formula is given here. All right, explicitly, the formula for the number of elk would be P naught, that's where we started, that was 12,000, right? Plus DN. D is 750, our common difference, how much it's going up each time, times the number of years. Oh, that's much more powerful, because if we want the year 2014, right, that would be N equals, let's see, if we started this off in 2003, right? When you think about this, 2014 minus 2003 would give you 11 years, right? 11 years of difference. So N would be 11 in the year 2014, 11 years since we started. So then we could say, oh, okay, so P sub 11, which is for 2014, would be equal to the 12,000 elk we started with plus 750 times 11 years. So let's do that. 750 times 11. I'm getting 8,250 plus the original 12,000 elk that we had. And you can see that in the year 2014, we would have 20,250 elk. So the population is growing quite a bit. And that's how it would work. Let's take a look at the second example, the gasoline example. And I have a graph that I brought in from the module, but we're going to see how to develop our own in just a second. So this one says gasoline consumption in the U.S. has been increasing steadily. Gasoline consumption data from 1992 to 2004 is shown below. Find a model for this data and use it to predict consumption in 2016. although 2016 is already passed, we could have used this to predict. We could also use it to predict the future. We know that trends change, but let's just assume that this data will continue. This trend will continue. All right, that's the assumption of the problem. And we're going to try and figure out when will it reach 200 billion gallons. Okay. So notice in the table, it's written into billions of gallons already. Okay. So we can see in 1992, we started off with 110 billion gallons. And in the year 2004, we have 136 billion gallons. Okay, so what's the trend? Well, if you just analyze the numbers, you're like, okay, that one's +1, and this one's, oh, wait, that one's +2, and that one's +3. Okay, but that one's +2, and that one's +1. Notice that these rates don't really seem to be linear, right? They're moving around. They're not the same. So this might leave you with some questions. So what you can do with this data is you can graph it, okay? And so I took the liberty of just using the graph from the text. Now, if you look at this graph, you can see that it's not like perfectly aligned, but there's kind of a linear, well, there is a linear trend, right? I can kind of draw a straight line through there and make this assumption that it acts linear. So what you would kind of want to be asking yourself is, well, does this look linear? Yes. So how can I assume, what do I assume that the linear difference is? Well, one way is to just analyze year to year, but another way to evaluate it is really just looking at like, okay, where did we start in 1992? And where did we end in 2004? And that might give us our overall trend. So let's just do that, all right? So let's take a look at the table. In 1992, we were at 110 billion gallons. In 2004, we were at 136. So if you subtract 136 minus 110, right, you're going to get 26 billion gallons, right? Increase, because you just take 136, subtract the 110, you get that. And then the thing to realize is like, okay, well, how many years did that take, right? Well, that was from 2004 up from 1992. So if we figure out how many years that is, that would be 12 years. It's easier to subtract than to count, right? You could count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That takes too long. So this is what we were basically using, 26 billion gallons in 12 years. So the average rate of change would just be to take the 26 billion gallons and divide by the 12 years. So let's do that. 26 divided by 12. It doesn't come out to be a nice number, so I'm going to round it. 2.1, and on the calculator, 66666. So I'm just going to round off to about 2.17 billion gallons per year of change. All right. So what that will be, this will act as our common difference, D. So if we want to use, I want to use the explicit formula, right, to find any term, we'll just take P naught, which is where we start, we'll add in the common difference plus the time number of years. So in this particular problem, right, we want to figure out, well, let's go ahead and write the formula first. So P naught is where we started. We started off in 1992 with the 110 billion. And then we've calculated or estimated D to be 2.17. I'll put that in times the number of years. If we go back to the problem, it asks, when will the consumption reach 200 billion gallons? It also asks, use it to predict the consumption in 2016. We're going to do both of those. So let's start off with the 2016. All right. So 2016 would be how many years from our start? Well, if we started in 1992, that would be a total of 24 years, right, from the beginning. So in 2016, we would say, well, P sub 24 is equal to 110 plus 2.17 times 24. I'll use a calculator for this. Now we have rounded off a little bit, but again, we're just making an estimate based upon the data available. So let's see, I'm getting approximately 100, I'm going to round off just to the nearest whole number, 162 billion gallons would be the projected consumption in the year 2016. The second question is, when will this consumption reach 200 billion gallons? And so that kind of more is a question of like, when will this total to the left? So we actually can create this algebraic equation. We take the 110 plus 2.17n, set it equal to 200, and solve this. So let's take a look at these steps. This is linear algebra steps. You might be familiar with these, and we'll end with this. So to solve this equation, we would do some inverse operations. The first step would be to subtract 110 from both sides of this equation. That may look familiar. And that will leave us on the left side with 90. And on the right side, we'll just be left with the 2.17 in. And then our next inverse operation is divide both sides by 2.17. And I'll grab a calculator, round this off. And I found the in is about 41. Again, I'm rounding off. I'm going to round off to 5. 41.5 years. What does that mean? Well, in 41.5 years, we'll be approximately consuming 200 billion gallons. Now, remember that this is years from 1992. So if we want to make it a little more real, just take 1992. We'll add 41.5. So it'd be the year 2033.5. What does that mean? Well, it just means about half of the way through the year, 2033, around June. Okay, hope that this helps you see how these two problems can be worked out in detail.